Okay, so hello everyone. So today I'm going to be telling you about fundamental theorems for free, logical relations, and parametricity for substructural type theory and beyond. And if you don't know what any of those words mean, yet don't worry, that's what we're going to be talking about. Um, but so maybe you've heard of like theorems for free in the context of like functional programming or type theory stuff like that, or maybe you've heard of parametricity in relation to that. But so like, what is parametricity? Well, it's when you have two metricities. That's a parametricity. No, I kid. Sorry. It's when you have a large urban settlement of parametries. That's a parametricity. Okay, no. But so to actually understand what parametricity is, what we're going to do is we're going to try to understand something a bit more general that parametricity is an instance of, and that's logical relations. So what is a logical relation? Well, if you go by a sort of textbook account, logical relations are a powerful proof technique that can be used to prove properties of type systems, such as normalization, canonicity, and parametricity, that typically evade straightforward proof by induction. So if you think about that, if you're at all familiar with any sorts of type theory where you might want to prove something like strong normalization, if you just try to do that by like a straightforward induction on the syntax, that doesn't work because you can have like interesting sort of loops in evaluation and stuff like that that could complicate that. And so logical relations are a way to get around that and basically kind of strengthen your induction hypothesis. And okay, so that's great, but but what is a logical relation? Well, so this is where things get a little kind of fuzzy because like the normal way of introducing logical relations is just by example, like you get shown some logical relations proof for like some simple type theory, and then you're sort of like asked to kind of imagine how you could kind of generalize that to other things. And so this lack of precision makes it difficult to extend logical relations arguments to novel type systems or more complicated ones, like dependent type theory or other sorts of interesting variations on type theory you could have. Since there isn't a clear standard by which to judge whether the relations you end up defining are actually the right ones. And so what I'm going to talk about here is I'm going to first off outline some of my own recent work that sort of highlights some of these interesting challenges, which is to do with proving parametricity theorems for substructural type systems, so things like linear type theory. And then I'm going to use this as a jumping off point to discuss a more general categorical recipe for logical relations that can be used to derive these and other examples, and really works for just about any type theory you can throw at it. And so I guess since today's the Valentine's Day special, the point I'm wanting to make is that logical relations and category theory are a match made in heaven. So without further ado, let's start with a quick recap of simply typed lambda calculus. And I'm not going to be super formal about defining syntax and stuff like that in this talk because it's not going to matter that much. And really the only main fact I need here is that simply typed lambda calculus is the internal language of Cartesian closed categories, i.e. we have an equivalence of categories like this, where STLC is the category of theories in simply typed lambda calculus, aka lambda theories, and translations between them. So those are things like you would have some signature in simply typed lambda calculus that says, okay, you have these basic types and these basic operations on those types and equations between those operations. And then that would include things like monoids, groups, and also more exotic things because in simply typed lambda calculus, we also have function types. So you can have interesting things that can model like general recursion and stuff like that as well. And then CCC is the category of Cartesian closed categories and functors that, in this case, strictly preserve finite products and exponentials between them. So technically, I'm doing Cartesian closed categories with a specified choice of products and exponentials for people who care about that. And then I'm asking that my morphisms in that category strictly preserve those. And that's because I want this to actually be an equivalence of one category, not just an equivalence of two categories. And so then this functor here that goes from STLC to CCC, sin, constructs the syntactic category for each theory in simply typed lambda calculus. So you take your simply typed lambda calculus, you take the syntax of it, and you build a category out of that by basically quotienting all the syntax by the equations you have in your theory. And that category is automatically Cartesian closed, where the exponentials come from function types and the products come from product types, as you would expect. And then L defines a theory in simply typed lambda calculus for each Cartesian closed category, and that's the internal language of that Cartesian closed category. And I'm not going to bother defining this because it's not going to matter that much, but it's basically you take for each object in your Cartesian closed category, you include a basic type in your theory, and then for each morphism, you have a operation in your lambda theory, and then you add equations to make it so that that is actually equivalent to the original category if you take the syntactic category of that. And so, okay, so that's all nice. And then, but let's look at something maybe just a little bit more interesting we can add to that, which is a natural numbers object. And so if we're in a Cartesian closed category C, a natural numbers object is the universal object that comes equipped with a point Z and endomorphism S. And so that's such that for any other object X with a point and an endomorphism, there's a unique morphism rec from the natural numbers object to X that makes this diagram compute. And so this morphism rec basically models primitive recursion on natural numbers. And so system T, which I believe is originally due to Gödel and the dialectica interpretation, adds to simply typed lambda calculus a type of natural numbers, which makes the syntactic category of system T the initial object in the category of Cartesian closed categories equipped with a natural numbers object, where now we're saying that the functors between those also have to preserve the choice of natural number object. And so one thing we can immediately ask about system T is, are the natural numbers that we have in system T equivalent to the actual natural numbers? Like if I do some complex calculation in system T that ends up defining some natural number, do I know that that actually corresponds to a numeral in terms of like, if you have some meta-theoretic number M, it has to be M applications of the successor to 0. And so this is the question of canonicity for system T. And indeed, this is a theorem, but just like proving normalization, this is hard. You can't do it by just straightforward induction on syntax, because again, it's basically you need a way of evaluating every closed term of type n in system T into a natural number, and that might involve some weird loopy evaluations, especially because we have this recursion construct that might be calling something arbitrarily many times. And so the proof of this theorem goes by a logical relations argument, which I can sketch for you really quickly. So what we're going to do is we're going to take each type in system T, and we're going to let this Scott bracket T be the set of closed terms of type T, tau, quotiented up to judgmental equality. And equivalently, you can think of this is just the points of type tau in the syntactic category of system T. And then for each type tau, we're going to define a predicate on this equivalence classes of closed terms of type tau as follows by induction on the structure of tau. So first, if something has unit type, it's in the predicate just in case it's equal to the unit element of type 1. If it's a natural number, then it's, or if it's an element of the natural number type, then it's in the predicate precisely if it is judgmentally equal to some numeral representing a meta-theoretic natural number. And so that's the thing we want for canonicity. And then for a product type, an element of that is in the relation if its first projection is in the predicate for the first type in the product, and the second projection is in the predicate for the second type in the product. And then this is probably the most interesting one, for an element of a function type, that's in the predicate for the function type if for all equivalence classes of closed terms of type A that are in the predicate defined at A, the result of applying f to little a is in the predicate for B. And so then once we've defined this, we get this fundamental theorem, or fundamental theorem of the logical relation. This is going to be a sort of recurring theme in all of these arguments, which is for every open term now, so remember these were closed terms, but now this is open terms, so those are terms that can depend on other, on variables of another type, or you can just think of these as these are morphisms in the syntactic category. And so for every open term, A, little a of type A in system T, for all closed terms of type gamma, if little gamma is in the predicate for gamma, then substituting little gamma for big gamma in A is in the predicate for A. And the way you prove this is just by induction on derivations, or the way you typically prove this is by induction on derivations. I'm going to eventually show you a way where you don't have to do that, because these inductions, as you can imagine, get quite hairy.
When you write gamma colon gamma, you really mean like element of the thing called square.
Yes, sorry, yeah, that's a slight typo there, but yeah. Okay, and then just to note, canonicity follows as a corollary of this fundamental theorem, because for any closed term of type n, you can just consider that as an open term that's just dependent on something of type unit, and then you have that term n must be in the predicate we defined for n, which was, again, exactly what we wanted to show for canonicity. So great. So that's a simple little logical relations argument. But now I want to do something a little bit more complicated, and this is where we get to start talking about some interesting things to do with parametricity. And so consider the theory, the lambda theory, lambda x, which is just the theory of a type. So we add just one basic type variable, big X, and that's it. And so this theory has the following universal property in the category of lambda theories, which is for any other lambda theory T and any type in T, there's a unique translation from lambda x to T that just substitutes A for X everywhere. And so we call a term f from A of X to B of X in lambda x a polymorphic function, since for any type C in any lambda theory T, we can obtain a function f by, oh, that should be C in there, sorry. But anyway, we just, if we have a function that's defined over X in lambda x, then we can substitute any other type for that and get a function of this corresponding type in any other theory, just by applying this translation here. So now intuitively, because we didn't assume anything about X in this theory lambda X, polymorphic functions can't inspect the type X over which it's defined. And so they have to behave somehow uniformly for all the types at which they can possibly be instantiated. But how do you even make that idea precise? And so the key idea that comes from John Reynolds is that polymorphic functions should preserve all possible predicates and relations you can define on types in simply type lambda calculus. And so the way we make that precise is, again, through a sort of logical relations construction. Let T be a lambda theory and C a type in T, and let some P, any subset of the closed terms of type C, and then for each type tau of X in lambda X, we define a new predicate, blackboard bold, P of tau, which is a subset of the closed terms of type tau of C as follows. So at X, it's just this predicate P here that we started out with. And then at 1, it's exactly the same as we had before. And oh, look, at the product type, it's exactly the same as we had before. And at the function type, it's exactly the same as what we had before. So the only thing we're doing here is now we're basically just adding this sort of base case to the induction, which can be pretty much whatever we want. And once again, we get a fundamental theorem of the logical relation, which says that for any open term in lambda x, for all ways you can substitute in for the domain of that, the result of doing that substitution is in the relation defined for A. And once again, the proof is by induction on the derivation of this in simply type lambda calculus. And so what's cool about this is this has a bunch of really interesting consequences, some of which you might be familiar with. So first off, we have this old chestnut. So every polymorphic function from x to x is extensionally equivalent to the identity function. And that just means for every possible function you can substitute in here and any argument you can apply it to, it just gives you exactly that argument back. And so let's see how we prove that. So by parametricity, we know that for any type C in any theory T and any predicate P on the closed terms of C, for all closed terms of C, if P of X of type C, if P of X, then P of alpha with C substitute for X applied to X. And hence for any little c and C, we just let P be the singleton set consisting of the equivalence class of C. And then by construction, we have that X is in P if and only if X is judgmentally equal to C. And so it follows that alpha with big C substituted for X applied to C must be judgmentally equal to C for all C and C. So alpha always computes to the identity function on every type you can instantiate it with. And so then, yes.
But we can't prove in that theory lambda x that it is there.
Right, yeah.
It just has that value, it has that effect on closed terms.
Yes, exactly. Yeah. And then, okay, so a further example, every polymorphic function of this type, so now we're taking in 2 elements of type X and giving back out 2 elements of type X, has to be equivalent to one of these 4 functions. So it either just has to return the elements it was given in the order it was given them, or it can swap them, or it can throw one away and return 2 copies of the other one, or vice versa. And so then the proof of this is going to be very similar to what we just did. So we can unfold the parametricity theorem for alpha to the following: for any type C in any theory T and any predicate, for any 2 elements x0 and x1 of type C, and such that P of x0 and P of x1, then we have that the first projection of applying alpha to x0 and x1 and the second projection both have to satisfy P. And so then for any C0 and C1, we just take P to be the set C0, C1, by which it follows that the first projection has to be one of C0, C1, and the second projection also has to be either C0 or C1. And then you can see by just doing a case analysis that these are the only 4 options you get.
Sorry to slow you down.
Yeah.
I'm always kind of confused by logical relation stuff where we start to blur the difference between functions and closed terms and substitutions of closed terms into functional expressions, which give rise to functions on the closed terms.
Yes.
And it's kind of, I think it's important to keep track of the difference.
Yes.
But I understand why people get tired of doing that.
Yeah.
And then drop the square brackets and so on. But like
the
last line, for example, it's like the function pi1 regarded as a term applied to closed terms using substitution results in a value which is in that set C1.
Yes.
C0, C1, which I guess means that the resulting substitution is beta A equivalent to 1.
Yes.
So,
Yes.
and like saying, so you define the polymorphic function
Mhm.
correctly to be a piece of syntax.
Yeah.
But then the notion of essentially equivalent is like, okay, the values of the function.
Yes.
As a function
Mhm.
on closed terms, it's equivalent to, or it's
Yes.
equal to.
Yes.
Equal to. Because now if we talk about as a function.
Yeah.
Then we don't have to say extensionally equivalent. It's just,
Yep.
it is equal to.
Yep.
The functions resulting from those expressions by substitution.
Yes.
So I'm just trying to sort this out a little bit to keep my head.
Yeah.
straight.
Yeah, no, that's good.
But
Yeah.
People who work in this area are used to that.
Yeah.
And then it becomes second nature to.
Yes. Yeah.
But maybe it's not obvious to everyone.
Yeah, no, thank you. Yeah.
So isn't there another step that you want to like get? I mean, it seems to me like what you proved is that for any closed terms, some type C, like for those specific closed terms, my function of that is like one of the 4 things it could be.
Yeah.
And I'd also like to know that maybe there's like, it doesn't depend on the choice of C and even the category and the closed terms and so on.
Yeah.
Which I can do by thinking about the universal example of such a guy. And then
Yeah.
this.
Yep. Okay. And so then, okay, so this is all great. This is cool. This is very well-known, well-trodden stuff. But now I want to talk about one thing I've been working on lately, which is extending these sorts of results to substructural type systems, which, so maybe if you've heard of stuff like linear type theory or stuff like that, and that raises some interesting issues that are going to sort of like motivate basically the whole rest of the talk. So to first talk about substructural type systems, I'm going to need to talk about monoidal categories. And so for just a quick recap here, this is not by any means a very rigorous treatment of monoidal categories, but so a monoidal category is a pseudo monoid object in cat, i.e. it's a category M that comes equipped with this unit element and this tensor operation, which are required to be unital and associative up to coherent isomorphism. And then a symmetric monoidal category is a monoidal category where we additionally have an isomorphism like this for all elements A and B, this natural A and B, that also has to satisfy some coherences. And then a monoidal category M is biclosed if for all elements of M, both tensoring with M with A on the left and tensoring with A on the right have right adjoints written like this and this respectively. And so let's have some examples. So any monoid can be regarded as a monoidal category with trivial morphisms, and likewise for commutative monoids and symmetric monoidal categories. And then also, perhaps more interesting for the purpose of this talk, a Cartesian closed category canonically carries the structure of a closed symmetric monoidal category, with the monoidal structure is just given by finite products. So this, the unit element is the terminal object, and the tensor is given by binary products. And that's symmetric by sort of well-known properties of products. And then it has, and then because it's symmetric, the order in which you tensor things together doesn't matter. So if tensoring on the left has a right adjoint, so does tensoring on the right. So both of these are just given by the exponential, as usual. And so then with this in mind, we can observe the following. So just like we defined simply type lambda calculus as the internal language of Cartesian closed categories, we can obtain substructural variants of simply type lambda calculus that will be the internal languages of different sorts of monoidal categories. So linear lambda calculus requires each variable to be used exactly once. So when you have multiple variables in a context in your typing rules in lambda calculus, this variant requires that they all have to be used exactly once. So you can't copy a variable and you can't throw it away either. And then ordered lambda calculus is even more restrictive than that. It additionally requires that variables have to be used in the order in which they occur in the context. So if your context is represented as a list, you have to use the variables in the same order they appear in the context. And so then ordered lambda calculus can be characterized as the internal language of biclosed monoidal categories, and linear lambda calculus is the internal language of closed symmetric monoidal categories. In that, once again, we have equivalences of categories, just like we had for simply type lambda calculus, like this, where now these are theories in ordered or respectively linear lambda calculus, and these are by closed monoidal categories and closed symmetric monoidal categories. And so then intuitively, if we're trying to get to sort of parametricity theorems for substructural lambda calculus, so linear and ordered lambda calculus are more restrictive than ordinary lambda calculus. So we would expect then to be able to get stronger parametricity results about terms in the former. And so for an example here, so if we just try to repeat the proof of parametricity for ordinary simply typed lambda calculus by considering the theory of a type X in ordered lambda calculus and define logical relations like we did before, this actually doesn't give us any new information over and above the parametricity theorem we had for simply typed lambda calculus. Because if we have, say, a function of this type, if you just run the same argument through, you can prove that it has to be extensionally equivalent to one of these four functions, but we can't deduce the stronger but correct result that in fact alpha can only be this one, basically the identity on pairs, if it's ordered lambda calculus, because this one's not allowed because it swaps them, and this one are not allowed because it copies something and also drops something. And so we need something more to make these parametricity, to get the parametricity theorems that we want out of this. And so the solution, which I came up with, I don't know if this is an original thought, but like I'm working on a paper right now about this. But so the solution is to parameterize our logical relations by a monoid. So if you just have a monoid M like this, then, okay, fix a theory T and a type C and T just like we had before. But now we have a relation, instead of just a predicate on closed terms of type C, we have a relation between elements of M and closed terms of type C. And then, just as before, by induction on types tau in this lambda X theory, we define a relation between M and closed terms of that type tau inductively on the structure of tau as follows. So at X, it just again evaluates to R. And then for a element of the unit type, now M is related to U if and only if M is equal to the unit of the monoid and U is equal to the unit element of 1 here. And then for an element of the tensor product, which are still represented as pairs in ordered or linear lambda calculus, we say that M is related to the pair consisting of A and B if and only if there exists some N and K and M such that M splits into N times K with the monoid multiplication, such that N is related to A at the predicate for A, big A, and K is related to B at the predicate for B. And then similarly for the this left exponential here, M is related to F if for all N in M and closed terms A of type A of C, N is related to A, or sorry, if N is related to A, then N times M with, we're putting N on the left, is related to the result of applying F to A. And then similarly for the right exponential, it's almost exactly the same, except in this last line, we put N on the right instead. So basically you can look at this and you can think we're basically using this monoid to kind of track where stuff is going and using the monoid to kind of simulate the restrictions on the usage of variables that we have in here. And this is just kind of following that all the way through. So then, once again, we get these fundamental theorems, both for ordered and linear simply typed lambda calculus, which look very similar to what we had before. So for any open term like this, and if we're an ordered SDLC, any monoid, then for all substitutions into the context of this term, if M is related to that substitution, then it's related to the result of applying that substitution. And then for linear simply type lambda calculus, it's almost exactly the same, except we just require that M is a commutative monoid instead of just an arbitrary monoid. And then the proof of both of these, again, is by induction on the derivation of this. And so, okay, so now what can we do with that? Well, let's go back to that example we had before. So now we can prove, I claim, that every polymorphic function of this type in ordered simply type lambda calculus must be extensionally equivalent to just this function. And so how do we do that? So first of all, I'm going to say let M be the free monoid on two generators, alpha and beta, i.e. the set of strings consisting of just alpha and beta, with the monoid operation given by string concatenation. Then for any type C and two elements, C0 and C1 of type C, we define R between M and C, closed terms of type C, such that M is related to X if and only if either M is just the singleton string consisting of alpha and then X is C0, or M is just the singleton string consisting of beta and X is C1. And so then by parametricity for digamma, we have the following. So for all M and N in M, if M is related to C0 and N is related to C1, then we have that digamma applied to C0 and C1 is judgmentally equivalent to a pair of this form with C prime 0 and C prime 1, such that there exist M prime and N prime such that M concatenated with N has to be equal to M prime concatenated with M prime, and R has and M prime is related to C prime 0 and N prime is related to C prime 1. So it's a bit of a mouthful, but if you then substitute in alpha for M and beta for N, what this implies is that we have these M prime, N prime, which have to be, because they're in this relation, they have to be one of alpha or beta, and such that the concatenation of alpha followed by beta has to be equal to M prime, N prime. And because this is just the free monoid on alpha and beta, M prime then has to be alpha and N prime has to be beta. And then because of the way we define this, that then implies that C0 prime has to be C0 and C1 prime has to be C1. And so then we get our desired results. And so that's great. So now we have this stronger parametricity theorem that we can use to prove more interesting parametricity theorems for substructural lambda calculus. But so now I want to take a step back and ask, how did I do that? Like, how did I know that A, sticking a monoid in there was a good idea, and B, that like all these definitions were going to work out, and I wasn't just kind of blindly guessing. And so basically, so I pulled the rabbit out of the hat, and I'm going to show you where the rabbit was all along. And to, I think, no one's surprise in this room, the rabbit was in the land of category theory. And so here's a question. So can we derive parametricity properties, can we derive parametricity from just some categorical properties of the syntactic category of this lambda X theory, rather than going by these laborious inductions on syntax? And so the key fact we're going to use here is that the syntactic category of lambda X is the initial object in the category of pointed biclosed monoidal categories. And so that just means biclosed monoidal categories with a designated object, and then functors between them that have to preserve those choices of objects. And again, strict functors between those. And so here's the idea. Given a monoid and a type in a theory T, and a relation between that monoid and the closed terms of that type, we will construct a pointed biclosed monoidal category of relations and derive parametricity from the existence of a functor like this, which follows from the fact that this category is initial. But so then how do we construct this category of relations? So we're going to need some categorical machinery. So the first thing I'm going to need is index post sets and the Groton deconstruction. So for any category C, we say that a C index post set is just a functor from C to posts, where post is the category of partially ordered sets. And then given a C index post set P, its Groton deconstruction is a category fibered over C, i.e. a functor like this, which is also a fibration, but we're actually not going to care too much about that particular aspect of it this time around, although it is important. And so we define this category integral of P as follows. So the objects of this are pairs consisting of A and P of A, where A is an object of C and P of A is an element of the post set P of A.
Wait,
yes.
So the C index post set, should the codomain be an actual post set, or is it?
No, it's a category. So yes, it's the category of all post sets. Yeah. And so for instance, so like this P of A here is a post set. And so I'm saying this little P of A is an element of that post set. And then a morphism from the pair A and P of A to the pair B and P of B in this category consists of a morphism from big A to big B, such that, which has this property, that when you apply the functorial action of this of P to F and move A along that to get something in P of B, then that has to be less than or equal to P of B with respect to the post set structure on P of B. And then we just define this functor pi here by it basically just projects out the first element and then projects out also these morphisms.
That's some chocolate if you want to draw a picture. Maybe you don't.
Yeah, well, you can see, but okay. And so, okay, so then one more thing I'm going to want is this idea of a lax monoidal Coprey sheaf, and that's a bit of a mouthful, so I'm just going to call that an LMC.
Yeah, please call that fractal.
What?
It's a fractal, it's not a Coprey sheaf.
Yeah. I just want to like make it clear that the codomain is set, basically. Yeah. But okay. Okay, I could also just call it an LMF. But okay, so anyway, one of these things on a monoidal category M is a functor from M to set that's equipped with coherent natural transformations. So we have this epsilon, which is a point of the set gamma at the monoidal unit, and this multiplication operation, which takes an element of gamma at A and an element of gamma at B, and then produces an element of gamma at the tensor of A and B. And those have to satisfy some coherence conditions, which I'm not going to bother with this time around. But so what I'm interested in here are some examples of LMFs like this. So for any monoidal category, the global sections functor, which consists of HOMs out of the monoidal unit in M, carries the structure of an LMC. And so let's see how that works. So first of all, we want a point of type for a point in the set HOM II. And any guesses for what that is? Yep, it's just the identity on it. And then we want this product operation where we want, if we have HOM IA and HOM IE, then we want to get a morphism from I to A tensor B. And so if I draw this out, that means we have some morphism I, some morphism from I to A, and some morphism from I B. And so then to get this, well, first of all, we can just, because the tensor product on the monodal category is a functor in both arguments, we can just first of all tensor these morphisms together. So now we have one from I cross I to A cross B. But then since I is the monodal unit, I cross I is just isomorphic to I. Yep. So so that's first of all this global sections functor, which is going to play a key role here. And then also any monoid, just a monoid in the category of sets, can be regarded as an LMF on the terminal category. So the terminal category is just trivially a monodal category because being a monodal category is like a two algebraic theory, and so it satisfies all the equations because everything's equal to everything else. But so then a monoid in particular, we have a unit like this and a multiplication map like this, and because the indexing here is trivial, these are all just the same set. And the coherences for a lax monoidal functor just reduced to associativity and unitality in this case. And so then also, given any two lax monoidal functors, gamma and delta like this, the functor on the product of M and N, where we just take the product in set of gamma of A and gamma and delta of B, that also carries the structure of a lax monoidal functor on now the product of M and N. Yes?
So is the lax part of it that epsilon and is also not isomorphism?
Yes, exactly.
Otherwise, if we weren't lax, it would be like the Hom I or the global sections functor. If it were like not lax, it would say something like this thing preserves.
Yeah, it would have to be. It would have to be that like a an element of the tensor type A tensor B is exactly or a global section of the tensor type is exactly equivalent to a pair of global sections of A and B, whereas in arbitrary monodal categories that doesn't have to be the case. And so okay, and then finally also if you have a lax monodal functor from N to set, and then a monoidal functor from M to N, so that's now a could be a strict monodal functor or even just one that's only up to isomorphism. But anyway, the precomposition of gamma with F also now carries the structure of a lax monoidal functor on M now. And that should intuitively make sense because since F preserves the monoidal structure on M and N, these operations and the equations on them should also all be preserved by precomposition. And so now we can start building our categories of relations. So first of all, I'm going to say let P be the functor that takes a set S to its poset of subsets ordered by inclusion. And note that for any functor from C to set, the composite of gamma with P is a C index poset.
Are you taking like the direct like the image as the hook reality, or what's this one off of it?
Yes, I am. Yeah. And then taking the Groton deconstruction of this composite then gives us a category fibered over C, which is just this. But if we look at this based on how we sort of define the Groton deconstruction, this is so what we have here are the objects of this are objects of C paired with some subset of gamma of A. So we have, and so you can think of basically the objects of this are like predicates on each of the sets gamma A for each A in C. And so this is equivalent to the full subcategory of this comma category, where we take set and gamma. And so this is also called the Fried cover or the Sierpinski cone. And it's specifically the full subcategory that's spanned by monic maps like this. And so this is like a sub-object in set of gamma of A. And so these are basically unary relations on gamma A for each A and C. And so we're going to call this construction here the category of relations of gamma. And so then the final piece we need here is the Day convolution, which says if we have a lax monoidal functor from M to set on a bi-closed monoidal category M, then the category of relations on gamma carries the structure of a bi-closed monoidal category over M. And so I'm just going to give a sketch of the proof here, but it's not that hard. So we define a bi-closed monoidal structure on the category of relations as follows. So the monoidal unit is just the pair consisting of the monoidal unit of M, and then the singleton set consisting of the point epsilon that we get from the lax monoidal structure of gamma. And then for A and B in M and subsets PA of gamma A and PB of gamma B, the monoidal product of the pair AP of A and BP of B is the pair consisting of A tensor B, because that's what it has to be, because we want, when we take the projection of this back down to M, it has to preserve the monoidal product. But then the thing we do with these relations is that we say, okay, this is the subset of gamma at A tensor B consisting of those X such that there exists some A in P of A and B in P of B such that X is equal to the multiplication of A times B, where that multiplication is what we again get from the lax monoidal structure on gamma. And then for the left closure of A and P of A and B of P of B, that's again pair consisting of the left closure of A and B, and the subset consisting of F in the set gamma of A to B, such that for all A in P of A, applying gamma alpha, where alpha is the co-unit of the adjunction between tensoring on the left and this A arrow functor, apply that to the multiplication of A and F, and that has to be in P of B. So if you think about that, what we're doing here is we have A, which is in P of A. So in particular, it's an element of gamma of A. Actually, let me draw this out. So we have A is in P of A, which is a subset of gamma A, and F is in gamma A to B. And so then first of all, what we can do is we can apply the tensor here, or sorry, the multiplication here. So this is going to be in gamma A tensor A to B. And then in M, because M's by closed, we have this co-unit map, which goes from A tensor A to B to B. And so then I apply the functorial action of gamma along this alpha to get that this is in gamma of B, and then we want to require that this should be in P of B. Make sense? Yeah.
So gamma is meant to be like pointwise monoidal structure. Is that right?
Yeah, kind of. Yeah.
And then rel gamma is meant to be like you bundle all these into a new thing, and you're showing that this new thing, like you're bundling like these pointwise monoidal structures into like one structure.
Yep.
Which you're now showing is monoidal.
Yep, yeah, exactly. Yep, or monoidal and biclosed. Because yeah, so this is we're defining right now the left closure of this category of relations. And then it's exactly the same for the right closure, except you put A on the right of F instead. And so then, but so the main point here is that this gives us a way of, once we have a Lax-monoidal functor gamma like this on M, we can always build this category of relations, which is then a biclosed monoidal category over M. And so now putting it all together, so given a theory T, together with a type C in T and a monoid M, and a relation R between elements of M and closed terms of type C, we first define gamma to be the following composite. So first of all, we're taking the global sections here of in the syntactic category of T, and we're crossing that with M, which is a monoid. So as we discussed, M can be regarded as a Lax-monoidal functor just from the unit, the terminal category. And then this global sections functor is always a Lax-monoidal functor. So their product also is a Lax-monoidal functor. So we have a Lax-monoidal functor from syn T to set. And then we also, and then because this syntactic category of lambda x is initial in the category of pointed biclosed monoidal categories, and syn T is in particular biclosed monoidal and pointed because we have a type C in syn T, then this is a monoidal functor. So then composing this with this gives us a Lax-monoidal functor from the syntactic category of lambda x. So we have our Lax-monoidal functor on this syntactic category by construction. And then applying day convolution yields a biclosed monoidal structure on this category of relations of gamma, which we're viewing as a category over this syntactic category. And then we also have that the pair consisting of X and R is in this category of relations because R is a subset of M times closed terms of type C, which again, recall, is equivalent to global sections of the type C. And then the objects of this are pairs consisting of a type in here and a subset of the result of applying this to the type and a subset of that. So we have an object in there. So this is also a pointed biclosed monoidal category. And so in particular, by the initiality of the syntactic category of lambda x, that gives us a pointed biclosed monoidal functor from the syntactic category of lambda x to the category of relations. And because this pi functor is also a biclosed monoidal, or sorry, pointed biclosed monoidal functor, the composite of those two is also 1, and it goes from sin of lambda x to sin of lambda x. But then since sin of lambda x is initial, there's only one endo map like this, and it has to be the identity. So this composite has to be the identity on the syntactic category. So what we have here is that this map here, this V' map, is a section of pi. And now, if we unpack this, by the fact that this is a functor for any function, so for any morphism in the syntactic category, which is just a function like this, we have that applying the Right. So this is going back to recall how we defined the root deconstruction. So we're saying that translating v dash of a of x along gamma applied at f applied at p gives us a subset of the relation defined at b. And if we unpack that further, what that means is for all elements of the monoid and all global sections, oh, that should be an I, of the type A of C, if M is related to A at the value here for A of X, then M is related to the precomposition of F by A, which is precisely the fundamental theorem that we proved earlier. And so now we didn't have to do a whole big complicated induction to get this. We just had to observe that this was initial and define some category that sort of cleverly packaged up all the definitions we were doing before. And so that's the sort of main idea for how, in general, you can use these sort of categorical technologies to get these logical relations arguments and make them a lot simpler than they would otherwise be. And so, taking a step back, we can now state a sort of more general recipe for logical relations, which is, okay, so if you want to define logical relations and prove the fundamental theorem for a given type theory T, first off, show that the syntactic category of T is the initial object in some category of structured categories C. Then, for a suitably chosen functor gamma from sin T to set, and some category of relations rel gamma, which should be a full subcategory of this Sierpinski cone of gamma, show that rel gamma is also an object of C, this category of structured categories, over sin T via the projection from rel gamma to sin T, and then derive the fundamental theorem from the existence of a section of this projection, which, as we saw already, follows from the fact that sin T is initial. So if you want kind of a general statement of, at least sort of in my book, what logical relations are, it's, let's say we have some two category C.
I'm confused by the use of the curly C there. Is that a generic object of these structured categories, or is it the category of such structured?
It's the category of such structured categories.
So when we say an object curly C over sin T, we mean not an object of, we mean category over sin T.
Yes, yes,
Which is a certain kind of structured category.
yes. Yep.
And rel is one of those things.
Yep.
Well, no, is rel an object of C,
Yes, it is.
of the category C? or
Yes.
of
Of the category C, yes.
C is like for each of those categories.
Yes.
Is that what's
The
going on?
diagram says.
Yeah.
And then rel is one of them?
Yes, exactly. Yep. Yeah. So the general sort of formulation of this is you have some two category C, and then you have some object A, which is in C. And then you have, or actually, let's make this a concrete two category. So it has some functor F down to cat. And so we have then some object A of C, and then we have some functor gamma, which goes from F of A to set. And then we want there to be some B, which is an object of C, such that f of b embeds faithfully in this Krinsky cone. And also the functor that you get like this to f of a is in the image of some functor pi, which goes from b to a. And then what you want to do, what a sort of like an equipment of a logical relations structure on A is just a section of pi. And so, and then in this particular case where A is the syntactic category of some type theory, we use the fact that that's initial in some in C, or carefully chosen C, to get this section automatically once we've shown that this category of relations is also an object of C. And so, okay, so that's my main punchline for this talk, but there's lots more potentially to talk about, and I think we have still almost an hour, so I'd be happy to take questions and discuss any aspects of this further. Let me just give you some potential things to think about for if you have questions. So the conclusion here is that category theory provides a general and powerfully simplifying language for logical relations. And what we've seen here is that this method can be used to handle logical relations for substructural lambda calculus, but there's many further applications. For one thing, if you just run this whole same story through, but now with the categorical semantics of dependent type theory, you can get logical relations for MLTT, Martin-Wolf type theory, and lots of other things like that. But so here are some questions that I've been thinking about, and I want to sort of like throw to the audience in case you want to talk about any of these further. So first question, what makes the day convolution structure that we defined on our category of relations the right one for this whole argument to work? And can we characterize that rightness with some sort of universal property? Because that would make this whole story even more sort of tight. And then, so particularly if you're interested in this, ask me about it. I do have some kind of sketchy thoughts that I'd be interested to talk further about. And then another question is, how do the forms of external parametricity, so everything we've talked about so far is external parametricity, because we're proving these parametricity results externally to the theories that we're looking in. But there's also, you can have type theories that have internal parametricity, where you can actually prove internally that, for instance, all functions of type for all x to x have to be the identity function. And so how does this sort of external parametricity relate to type theories with internal parametricity and their categorical semantics? And that's what I'm going to be talking about at my next talk here. So look forward to that. But also, if you have any questions about that in the meantime, please don't hesitate to ask. And so with that, I'll say thank you, and hope to, if you have any questions, please run them by me. So. Yes.
So you kind of answered this with one, but when you motivated this, you talk about the relations arguments, that it wasn't clear that the definition of the relation is the right one.
Yeah.
It seems like that has been now, like the right thing.
It's been now moved up one level.
Right. So
yeah.
It's now like rel, like this category, right? Rel gamma.
Yeah. Well, I think rel gamma is like for just some functor gamma is like pretty much the only thing it can, or well, you have some leeway because you don't need it to be, it doesn't need to be a full subcategory of the Sierpinski cone. It could just be the Sierpinski cone. And that would give you like proof relevant logical relations, because now instead of just a sub-object of this set gamma A, you just have some set that maps into gamma of A. And so that's like a gamma A indexed family of sets. So so you have some wiggle room here, but like within this sort of like thing that it should be some subcategory of this, possibly including just this. I think that's fine. But then the place where this becomes interesting is when you want to define a monoidal structure on this. So monoidal structures on categories aren't necessarily unique. You can have multiple inequivalent ones. And so this day convolution one is in general just one of them. If we were doing this whole story instead for not for linear lambda calculus, this problem wouldn't arise because the day convolution would actually give you the product and the exponential, both of which are defined by universal properties, so they're entirely unique. So your hand is completely forced in that case. So it's only so that's what I'm trying to understand better is like, so where does this day convolution structure come from, and sort of what's its universal property that makes this work?
Let me try to attack this.
Yes.
By reformulating the construction
Yes.
here. So if I remember correctly, a lax monoidal factor from a monoidal category to set
Yes.
is a monoid object for the deconvolution
Yes.
in the category of covariant factors. In
Yes. Yes.
And so another construction of this slice here, or the rel thing, the rel gamma thing, is as a fiber product of I take M, I embed M. Maybe I want M out, or maybe there's going to be a variance issue, but so I want to look at a category of functors from M to set. So that's a monoidal category for the day convolution.
Yes.
From M. And a monoid in this category, it's the same as your MMCs.
Yep.
And now, so we have this category, this monoidal category, and we have a monoid inside. When we have a monoid in a monoidal category, the slice category is monoidal again.
Yes. Yes.
And so we can look at the forgetful functor from the slice over the monoid gamma onto this category of functors M into set. And then we have the unit embedding of M up into functors into M into set. And which is monoidal by definition of the day convolution. And so we have a pullback of monoidal functors. I mean, we have the co-span of monoidal functors. And if you take the pullback, I think this is your rel.
That makes sense. Yeah, I think that's right.
And so it seems like we were interested in monoidal relations because of this example of sorry, I forgot the name that you gave to this. The directed
ordered lambda calculus. Yeah.
Ordered lambda calculus. So if we were thinking of some other logical theory, like just having Cartesian products. And then would okay, not every object is going to be a monoid for the Cartesian product. So that's, I'm trying to adapt this setting to other contexts than the monoidal ones.
Yes, yeah, me too. That's how I've been trying to think about this.
Because every kind of category with structure, provided the structure is algebraic, like a monoidal structure, or even which is closed or not, the forgetful functor to cat will preserve limits. And so we'll create limits.
Yes.
And so that's why this pullback, this is always a monoidal category. It has always the structure that whatever the three other guys are going to have. Sorry?
I want to see the pullback.
Sorry. Yeah, maybe I should have. Let me try to do it here. Can you read here? It's terrible. This ball is terrible with this one. Is it better? Right? Oh, yeah. It's better. So we have our monoidal category M, and I look at fractals from M to Z.
Yeah.
Because M is monoidal, I can extend, so this is the Frico completion of M up.
Yep.
And so I have a monoidal structure here. So I can freely extend my monoidal structure by commutation with the colimits. And so that's the day monoidal structure in this category. So by definition, the unit embedding is monoidal, strong monoidal. And then I extend to arbitrary fractals by describing those fractals with their elements, and then multiplying the elements and then taking the colimits. Now, if I have the slice of a monoidal category, it might not be monoidal anymore. But if gamma is a monoid, then it is. Because I have two objects over gamma, I can define a multiplication using the monoid structure of gamma. So, and the forgetful fractal becomes monoidal. And so this is a monoidal fractal, not lax monoidal, an actual monoidal fractal. This is also actual monoidal. And so I can compute the pullback in the category of monoidal categories and monoidal fractals. And I claim this is the real gamma, maybe with an op.
Okay.
Yeah.
And so whatever structure exists here is going to be inherited here because it's a pullback of structured category. So
yeah,
the computing the pullback in CAD creates the structure that we have. So if we want to generalize this to other settings, whatever structure M has must be preserved by the unit I'm embedding. That's easy enough, provided the structure does not concern colimits.
Yes.
If it concerns colimits, then maybe we need to localize this category so that it concerns, if we have finite sum, for example, then we might want to do something. I don't know. So here we have an up, so maybe we can put the up here. I don't know. In a monoidal setting, that doesn't really matter.
Yeah.
But if we think of M as a Cartesian category, then it does. So
yeah,
I'm assuming maybe it could be best to use an up here. I don't know.
Yeah.
Anyway, so the unit embedding usually is kind of nice. It preserves for free a lot of structure for everything that has to do with limits is going to be preserved for free. Now the question is, when is a slice preserving that same structure? So that's not always the case. So that's a condition on gamma.
Yeah.
So we're going to need a gamma satisfying some condition which depend on the structure that you're interested in.
Yeah.
Such that this fractal preserved that structure becomes a morphism in the whatever in the category big C. And then we take the pullback and we have something with the same structure.
Yep.
Now this just, I mean, I don't know how to continue that. But it looks like that's the way that I have to understand your construction.
Okay. Yeah. That's great. I will.
I think this pullback is not real yet because this is I can do this. It's like an object of M.
Okay.
And then I have its image under your data, and then I ask also to have a map from that to gamma. Right. So it's just an object of M and an element of gamma.
Okay, you mean that's the wrong? It's not the good pullback.
There's another step in this construction where you look at the power set. Like the actual rel is like an element of M and a subset of it.
Yeah, that's the doing.
Yes, right. Yes, you're right.
This part.
So we can take gamma and we have to transform gamma. It's not gamma that we want. It's the free sublattice on gamma. And that's what the P is doing. And so maybe we don't. So if I have a monoid and I look at the subset of my monoid, it's again a monoid.
Yeah, also ridiculous.
And I think this is the thing that is used.
Yeah.
And that's I think that's the meaning of
Yeah, if you go back like
construction
slides or so.
right.
There was there, right?
Yeah.
Gamma equals covariant power set.
Yeah, so yeah, you're right. We need to. So my gamma is not this gamma. It's yes, it's composed with something else. And maybe so. Maybe a more correct picture is to look at both sets here
Mhm.
and P of gamma instead of gamma.
Yeah.
And then it should be the good category.
And maybe now it's another thing you could take besides the strict or besides the pullback is the comma square. And that would also.
So yeah, you could take the comma square and then you need only the object gamma.
Right.
You need the thing pointing at the object gamma in the bottom category.
Oh,
And then you take the comma square and that's the same.
Mm.
I see.
But the question is, when is the comma square is going
Okay.
to, when the comma square does not preserve automatically the structure.
Yeah.
Because the morphism from one pointing at gamma is not in the category.
Oh, I see.
That's why I use the slice.
I can say a little bit about like what, when I was trying to think about this, where my thoughts were headed. This seems very nice. I really want to look into that and see if I can push that further. But so what I was thinking about was looking at the Sierpinski cone, which was, okay, so which was this comma category, right? And remember we defined gamma. I'm going to be slightly sloppy here and say gamma. It was a little more complicated than this, but it was morally it was just this product of this global sections functor and M, where M is a monoid. And so then that should be equivalent to set to the M down arrow like this. And so what this possibly suggests is if C is nice enough, like if it's from if it's a category of models of some like 2 theory, let's say, it'll have comma objects. So that means this part of the construction is basically something you get for free. So the only thing that sort of leaves to answer is what is the sort of like general universal property of this in C, and which sort of theories have an object with that property. Because like, so this can be viewed as an object of C if C is monoidal categories, where this is has the deconvolution.
Yeah.
And so what I've been thinking about with this lately is in terms of how you get C if instead of or you think of C as, I'd say that C is actually, well, so first off, C is now a virtual, sometimes, double category. And in particular, it's the virtual double category of models of some double theory T, where that's in the sense of Lambert and Patterson's paper on double theories. So in particular, it's the virtual double category of double functors horizontally lax, or this H lax, horizontally lax double functors from some double category D to span. And so this covers in like, so Lambert and Patterson's paper they did Cartesian double theories, so double theories with all finite products. And so that gets you, you can define monoidal categories this way, monoidal, and also, I think you can do closed monoidal categories, because I think you have enough stuff in there that you can define dual objects. But so anyway, and it gets you a lot of other sort of categorical structures you can define that way. But so, okay, but the punchline to this is that this is actually a double category because any one of these theories, sorts of theory, right? So the theory is just the indexing double category. And it gives us a notion of, so if D is our theory, is our double theory. Then we get a notion of a D profunction, which is just a horizontal transformation between two things in here. So this is like, so if you have like.
So can you give an example where C, like, I assume that if I started with, let's forget the by closed part, just.
Yeah, just monoidal,
Monoidal category,
yeah.
monoidal category, which one do you prefer? I assume that this new C is like some enhancement of the old by category or whatever.
Yep.
Monoidal categories to a double category. Could you say what it is? Like,
yeah.
one of the arrows must be the ones we know, and then the other arrows must be some other thing.
Yeah,
like,
yeah. So yeah, so okay, so the objects, okay. So yeah, so for monoidal, I'll do monoidal categories. So for monoidal categories, objects are monoidal categories, as you would expect. That's the vertical arrows are monoidal functors. Go right vertically. This monoidal. Yeah. Okay. Or you get different flavors. You can have them be strong or lax or whatever, and that might be relevant at some point. And then a horizontal arrow is a monoidal profunctor. Call it P. And what that particularly is that's one where you have a natural transformation that goes like PAB times PCD goes to B A tensor C B tensor D.
Looks like your last one, I appreciate.
Yes, yeah, exactly. So yeah, so one half of this, and then the theorem that you get is precisely that one of these, a horizontal arrow, monoidal profunctor from M to N is equivalent to, oh, and let me just write out the signature of this. So it goes from M off times N to set. And so then one of these is equivalent to a lax monoidal functor. So what I've been playing with is that if you have something where you have a notion of pro arrow like this, which you do automatically get from these double theories, you can at least define what the universal property of this should be, which is that it should be basically a classifying object for horizontal arrows.
The one already pointed out, is think of gamma now as a horizontal arrow from 1 to m or 1 to n1.
Yeah.
Does the rest of the construction also translate into some things we do?
I mean, it should, like, I mean, basically it's, I guess like, for all the examples that I've tried this on, like, you take your type theory, you know what sort of class of categorical things are its models. You run that, whole thing, through this, and it gives you basically exactly the logical relations theorem you would have wanted to prove things like canonicity or parametricity. So if this is correct, then it's basically a way of sort of generalizing the notion of parametricity to any class of structured categories that can be at least described as models for those sorts of theories. That where the one additional condition is it needs to have basically like these things. The category models needs to have like, or double category models needs to have these sort of classifying objects for horizontal arrows, which that
Yeah.
is, yes?
That's just a free thing. So I think if I understand how the double category setting is working here, it's just we use the pre-sheaf completion here.
Yes.
And so that's where this double category, that the example of double
Yes.
category is coming from. I think
Yes.
it's just a double category suggested from functor to cat, which is
Yes.
the pre-sheaf construction.
Yes. Yes.
Instead of looking at it as a functor from cat to cat, you look at it as a double category.
Yes.
You get this double category. So
Yes, I think that makes sense.
I think it seems like what we need is a monad.
Yes.
And it's a free completion of something,
Mhm.
which is this pre-sheaf
Yep.
thing in this example. And
Jonas isn't here. I'll point out that it's not just a one, but a lack of input.
Right, yeah, yeah.
okay, Jonas is here in spirit. Okay, well, I don't know where in this enters the construction here, but why those codecs or
Yeah.
only Jonas?
Yeah. Yeah.
In the usual logical relations arguments, at least when happy understanding them,
Mhm.
there's a global sections functor interset and
Yeah.
then glue along that.
Yes.
And that gives us the fried cover or
Yep.
Sierpinski cone.
Mhm.
And then that has a projection which preserves all the structure.
Mhm.
And if we're doing this to the initial
Mhm.
such category, the free one.
Yep.
Then that's a section of the
Yep.
projection. That's how
Mhm.
it goes like the Fried's original
Mhm.
for maybe the existence and disjunction properties for hiding arithmetic.
Yep.
And then there are other
Yep. Mhm.
more sophisticated variants sometimes involved. So what you're doing is you're doing something like that as a first step.
Mhm.
And then you doctor things up.
Yep.
And I wonder if it's not possible to reverse the order of those two things and
Mhm.
glue not along a functor into set,
Mhm.
but along a functor into M sets. Or something like
Yes.
that, for a
Yeah.
simple monoid.
Yeah.
So first you do your doctoring up,
Mhm.
and then you do the gluing in a more
Yeah, I think that
setting.
yeah, I think that's actually basically what I'm
Yeah.
doing there, because
Looks like
the
when I did that, like
yeah.
transpose to the
That's
M
what-
onto the,
That's
yep,
what I
yep.
think. Maybe we're gluing, we have a functor that goes into M sets.
Yep.
And then we're gluing along that.
Yep. Yep.
And that might be another way of understanding the setup, which at least brings it in line with a more familiar proof approach.
Yes.
Seems to me.
Yep.
And this kind of lines up also with some of the proofs that have been given for canonicity for dependent type theory, like
Yep.
cubical type theory
Yep.
and so on.
Yep.
Where they glue along a functor that's not going into set.
Yep.
But it's like functor into cubical set.
Yep.
So then they glue along that.
Yeah, yeah, that was exactly what I had in mind when I was thinking of this. So yeah. Yeah. What?
You can see, where, I didn't want to interrupt you.
Oh, sorry, did I interrupt?
No,
No.
I wasn't interrupting.
Yeah.
I'm
I just wanted to note, this kind of reminds me more of graded type theory than linear type theory. Where you have
How's that?
gradients associated with the one.
Mhm.
That's kind of your model.
Yes, I mean, so that's another thing that I've been thinking about. So there's at least like, so for linear logic, there's at least the resource semantics interpretation that basically says that like if you translate linear logic into the theory of the intuitionistic theory of a monoid under the resource interpretation, that's sound incomplete. Um, I'm not sure if anybody has actually proved the analogous result for linear type theory. But I wouldn't be surprised if it was the case. So I mean, and what I'm kind of, that's sort of one thing that I'm kind of, I guess another thing that I'm sort of implicitly appealing to here is that when we have something like we have our syntactic category, which is initial in this big C that we've been talking about, which is some category of structured categories. And then we also have these sort of appreciate categories, and such that for any monoidal category M, there's this polynomial embedding of M into set M op now. And so when you have something like this, where you have an initial object in a category with these sorts of objects, I think you should be able to get a completeness result that says that like something is there exists a such and such thing with such and such properties in this thing, if and only if the corresponding thing exists in all categories of this form, which I think should suffice to basically give you a completeness theorem that would say that what I'm doing here kind of because this is sort of like the graded interpretation. And so this sort of suffices to say, okay, what I'm doing here is like also sound complete for that.
I mean, it seems to me like you could frame this all like you're doing logical relations for graded type theory. And getting this into similar to this.
Yeah.
And then it just so happens that graded type theory and linear type theory or theory play nicely together.
Yes.
But it seems like fundamentally this techniques is all about graded. I don't know.
Yeah, it is all like indexing by a monoid and stuff like that. So yeah, that's interesting.
Yeah, I mean, that was the thing that struck me as most mysterious. But you had, I remember you had maybe a couple slides again ago, you had like bold idea and then like suppose you have a monoid M, but then how do you know before this?
I think it's all the way back here. Yeah, solution is to parameterize several logical relations by a monoid M.
So why a monoid? Somehow we extracted this from the concept of a bicolor monoid.
So I'm not oh right, yeah. So
somehow since the answer is whatever works to prove the like we could have used some other kind of thing, but we were interested in the end of proving this like that all functions of the type X,
Yeah.
X, blah blah blah. So we just turned out the minimum thing we needed was a monoid maybe.
Yep. Yeah, I mean that is the actual practical, that is how it actually arose for me. I think I was thinking in terms of some of the motivation for this at in the back of my mind, I have like, okay, in general, this doesn't actually need to be a monoid, it could be a monoidal category.
Yeah.
And so that's and so I'm just but I'm actually like I'm interested to know if like actually just restricting to monoids suffices.
Right, and is that like a version of a completeness theorem?
Yeah, exactly.
Need to think about models.
Yeah, exactly. So that's something that I haven't answered for myself yet, but that I'm very interested in. Yeah.
Like the parameters we picked for relations are the same parameters we picked to get a class of models that are repeat for the theory.
Yes. Any other questions or comments?
I guess sort of on the point about the line, I mean, the important thing in the proof it seemed like was that it's not conditional.
Yes.
So you couldn't extend it to like a group. Like a group.
Yeah.
And done the same thing.
Mhm.
But you couldn't have like taken the three communities of line.
Right, yes. Yeah, exactly.
How do you feel about, I mean, you also don't need the unit, I guess.
I think it comes up in other examples. Or yeah, it does come up in other examples.
Unit is possible.
Yeah, exactly.
Okay, well, thank you, CB.
Next week,
Next.
what is next week?